Assalamualaikum dan selamat sejahtera. So we continue our lecture on heat transfer. So this is essentially an introduction of heat transfer. So the objective for this topic is to understand how thermodynamics and heat transfer are related to each other. So because you have learned thermodynamics before, and then understanding the three main principles of heat transfer, which is conduction, convection, and radiation, and to identify mechanism of heat transfer. So we'll be learning about the modes of heat transfer, the basic concept of heat transfer, and why we need heat transfer since we have learned thermodynamics. So in general, heat travels from high temperature to low temperature. Okay, so the travel of heat can be done or follows these three main heat transfer: conduction, convection, and radiation. But they are all related to transfer of energy from high to low. So form of energy is transferred from one system to another system as a result of temperature gradient. So if you look at this example, so we have hot coffee, which is the temperature 70 degrees C, and cool environment 20 degrees C. Because the coffee is hot, so energy transfer from hot to cool. Okay. So naturally, it can be done, right? But if you want to transfer energy from cold to hot, so we need an external device to do it. So I think we have learned this in a thermodynamic second law, okay, how to transfer energy from low temperature region to high temperature region. But let's keep it on heat transfer side, not on the second law of thermodynamics. So the thermodynamic is the foundation of heat transfer. So that's why we need to learn thermodynamics first before we can embark our knowledge on heat transfer, which is we need energy balance and knowledge from thermodynamics to the heat transfer. So we have three modes of heat transfer: conduction, convection, radiation. Okay, but for this topic, okay, in general of heat transfer, we are going to be learning conduction and convection. So what is conduction? So it's basically a transfer of energy from more energetic particle of a substance to the adjacent less energetic ones as a result of interaction between particles. So the energy transfer is due to different temperature causes by vibration of particle in a solid. So in liquid or gas, because the molecule or the molecule can randomly move. So how does the energy transfer? Is due to collision and diffusion. Okay, in solid due to vibration. So the rate of heat conduction through material. So let's assume this is the example from hot to cold. Depends on the thickness of the material, the type of material, and the temperature difference that we apply on the material. So if we plot the temperature against the length of the bar, so let's say we heat it on one side and we leave it to ambient at the other side, so we'll have a temperature profile. Okay, in this case, we have negative slope, depending on your the axis of the datum of your x-axis. If you put this 0, then you should be starting your t over here. So it doesn't matter. So heat transfer through conduction is governed by Fourier's law of heat transfer. Fourier's law of heat conduction. Sorry. So mathematically represented by this equation. So Q conduction is equal to minus thermal conductivity of the material, which is K, the effective area, in which this cross-section area, and the temperature gradient dt over dx. So dt over dx is basically this one, the line of the slope. So for heat conduction, so you're going to be using this equation. Okay, so the question we will raise, I believe you will raise why we have negative over here. Okay, so heat is a vector unit. So it has magnitude, it has direction as well. So if we decide the heat transfer to the right side to be positive, okay, to be positive, uh, that's why we have negative over here, because the temperature profile has a negative slope. Okay, so if you calculate dt over dx over here, you will be getting a negative dt over dx. So negative multiplied by negative, you have positive. So you q heat transfer, heat conduction is going to be on the towards the right hand side. So that's why we have a negative over here to basically determine its direction. Okay. So convection is transfer of energy between a solid surface. Okay, let's say this is solid surface, and the adjacent liquid or gas that is in motion. This is the important word, or the key word of for convection. Must be the fluid must be in motion. So in general, convection is a combination of conduction and fluid in motion. So let's say you have a jar that you fill in water. The fluid stays stagnant. So the heat transfer will be conduction because the fluid not in motion. So if you observe that the fluid starts to have this kind of behavior, so or in motion, so the heat transfer going to be convection. So this is the keyword: liquid or gas in motion. So convection heat transfer has two mechanisms. So random molecular motion or diffusion, bulk motion of fluid or convection. So when both are present, we call it convection. So basically a combination of conduction and part of convection. So we have conduction over here and we add advection. So the combination of these two, we have convection. So for heat transfer by convection is governed by Newton's law of cooling. So this is the equation for convection, in which the H is heat transfer coefficient. So how the strong of the flow, okay. T as the surface of the material, the heat transfer of the heat transfer that we want to calculate on the material. T ambient is the ambient next to the material we want to calculate the heat transfer through convection. So the last one is heat transfer via radiation. So it's basically energy emitted by matter in form of electromagnetic wave. So as a result of changes in electronic configuration of the atom or molecule. So basically thermal radiation. So energy emission from a matter at a finite temperature. So basically we need to have two finite temperature. Let's say we have the temperature of the sun, we have the temperature of the earth. So this is the finite temperature, assuming. So if we have the finite temperature, we can calculate the energy transfer via radiation. So radiation can be transported without no medium, in which it can be transported in a vacuum. So for conduction and convection, it cannot be transported by a vacuum. So it needs, for conduction and convection, it needs medium. But radiation doesn't need medium to transfer the energy or for heat transfer to occur. So all solid, liquid, gases emit, absorb, or transmit radiation to a varying degree. So it depends on the material of the property. So the radiation is governed mathematically by Stefan's Boltzmann law. So this Q dot emit radiation is equal to the sigma, which is the constant. The value doesn't change. This is the fixed value. This is constant for the sigma. So AS is the surface area of the radiation that you want to calculate, not the cross section. Okay. T to the power of 4 is the surface temperature. So if this is a general equation for Stefan Boltzmann. If you consider the material of the material in which the heat transfer to radiation occur, so we have this small e, which is emissivity. Okay, so if you have emissivity close to 1, so you will have a high amount of absorption of radiation. So you can find your emissivity here. So that's why most of the construction, especially to build a roof, you put aluminum foil underneath the roof because we have emissivity very low. So if you plug in here, so the absorption of the radiation can be reduced. Okay. So in general, black body is a perfect absorber and a perfect radiator of energy with no reflecting power. So black body is an opaque body which can absorb 100% radiation and emit 100% of radiation. All right. So we have learned thermodynamics before. Why is not enough? So if we focus on thermodynamics, so basically thermodynamics tells us about energy transfer between the system and surrounding. But most of the time we are in equilibrium state. If you want to ask yourself how long does the process take place, you cannot answer by thermodynamics. But you can calculate the amount of heat transfer. By studying heat transfer, you can know the rate of heat transfer, and we now can identify the mechanism of heat transfer. But heat transfer is not an equilibrium phenomenon. Therefore, you can calculate how long the process it takes for a certain process to achieve. It also can tell the amount of heat transfer. So thermodynamic, we deal most of the time about work and heat that crosses the boundary. But how long the process takes place, we cannot answer solely by thermodynamics. So we need the help from heat transfer. In heat transfer, so we are dealing with the movement of heat from one side to the side. As a result of that, we will be having temperature gradient along the line. So if we have this kind of problem, so we have a hot coffee, we insulate. Okay, so if we put ourselves from if we view this from the thermodynamics perspective, so let's say we have the coffee initially at 90 degrees C. We want to we allow the coffee to cool down until 70 degrees C. Okay, so for thermodynamic, we can calculate the amount of heat transfer from 90 to 70 degrees C. But what is the method of cooling? So we don't know from thermodynamics. If we view this problem from heat transfer perspective, so we can actually calculate how long does it take for the hot coffee to reach 70 degrees C from 90 degrees C. And we can also provide a way of cooling or heating. So in essence, so heat transfer is all about answering the following question. What is the heat flow rate from A to B? Okay, from hot to cold region, depending on your problem. So consider a can of drink which you want to cool down. You put in the refrigerator. Initially, you buy a can of drink, 20 degrees C, and then you put on your fridge. Your fridge temperature is 4 degrees C. So we know from experience that we leave it in the fridge. So ultimately, we reach equilibrium with its surrounding. In which, if you place your can, your soda in your refrigerator, eventually the temperature will reach 4 degrees C. But how long does it take? So thermodynamic cannot answer that. That's why we need heat transfer. So this is the summary of the heat transfer mechanism we are going to learn. Conduction governed by Fourier's law, convection Newton's law of cooling, radiation by Stefan Boltzmann law. Mathematically represented by this equation, okay, for Fourier's law, by Newton's cooling by this equation, and radiation by this equation. The most important parameter for Fourier's law that governs the rate of heat transfer is at K, thermal conductivity of the material. For convection is H, convective coefficient. For radiation is emissivity of the material. So you can read this from your textbook in detail. So this is just summary of it. Okay. All right. So simultaneous heat transfer mechanism. So heat transfer is only by conduction in opaque solid. So what is opaque solid? Opaque solid is a material or solid that light cannot pass. Okay, so basically solid. So by conduction and radiation in a semi-transparent solid. So the heat transfer only by conduction in opaque solid. Okay, the heat transfer by conduction and radiation in semi-transparent solid, and heat transfer to a vacuum only by radiation. Okay, since conduction or convection requires presence of material medium. So if we are dealing with opaque solid, the heat transfer internally of opaque solid is through conduction, only one mode. For gas, it can be radiation, it can be conduction or convection, combination of radiation and conduction, or combination of radiation with convection. In vacuum only, radiation. So that's what it means by simultaneous, where you have two mechanisms occurring at the same time. So heat transfer through a fluid, we can have either conduction or convection, but not both. So if you have a motion of fluid, the heat transfer going to be convection. If no motion of fluid, the heat transfer going to be conduction. So let's say your body temperature right now is 29 degrees C in the relatively cool room, so 20 degrees C. What happens? You will transfer heat from your body to the environment, because we are transferring heat from hotter region to a colder region. So the method or the mechanism of heat transfer, in this case, we have two mechanisms that are occurring simultaneously, which is convection and radiation. Okay, so for convection, this is the equation related to convection. Okay, so this is heat transfer mechanism, heat transfer coefficient, which is 6. Okay, this is a surface area, effective surface area of the body, and T surface is surface of temperature of the body. T ambient is the ambient temperature. And equation for radiation, this is the equation for radiation. As you have emissivity of the body, the sigma, which is the constant, Stephen Boltzmann constant, surface area, the temperature surface of the body, and the surrounding. So because the heat transfer occurs simultaneously for conduction and convection, so the total heat transfer will be convection plus the radiation. So you have 168 watt. So in general, or the principle, we are dealing, we have mass, we have momentum. So in heat transfer, we are dealing with only conservation of energy. So we are not dealing with mass and momentum. So how to analyze heat transfer? In general, we need to draw the diagram, the heat transfer from point A to point B, okay, and state the non-variables. And then we decide what must be found or what need to be calculated. And then we need to list all the assumptions. So heat transfer involves lots of physical property. Thermal conductivity of the material, heat transfer coefficient, and immiscibility. So you need to compile the physical property from a table. So we need to develop, for analysis, we need to develop analysis before applying numerical value. So we need to calculate heat generation, and we need to determine the heat direction, and finally underline the constant. Okay, let's answer some of this. So if a fluid stands still, what's the mode of heat transfer? So fluid, if you're talking about fluid, the heat transfer mechanism will be convection. But since the fluid stands still, so the heat transfer going to be a conduction. So what if the fluid is in motion? So the answer will be convection. Can we have conduction and convection in a fluid? So if you go back to this, okay, heat transfer through fluid, we have either conduction or convection, not both. So only one in fluid, either conduction or convection. Okay. So what mode of heat transfer through a vacuum? This is going to be radiation. How many mode of heat transfer through a solid? Through a solid going to be one, only conduction. So the importance application of heat transfer. So for calculating efficiency, so most of engineering work involves high temperature. So we need to calculate the heat transfer rate. So that's why we need to learn heat transfer. Okay. For batteries, for energy recovery, even though batteries is considered electronics, so, but it generates heat. So we need to know the heat transfer rate in order to make it safe. Okay, but important thing is we want to control, right? So if you are working with high energy density stuff, so that's going to be high heat transfer rate, so we need to control. So without power without control means nothing. Okay, so that's why the important thing to learn heat transfer, because we want to know the rate of heat transfer and the time it takes from heat transfer to occur one uh, from one temperature to another temperature. So this is what I did before during my PhD, that involved heat transfer, removing heat from the cell to make it isothermal, and then I did some image image capturing with respect to temperature. So in general, we need to control them. So by studying heat transfer, we'll know which point in this, let's say turbine cooling, so which point going to be a hot spot. So you need to reduce the temperature via cooling. Okay, so your knowledge of heat transfer will help that a lot. Okay, also in biomedical, right? So to determine some infection or to predict tumor based on a temperature variation. So building is most commonly used heat transfer. Um, all right, so that's all for introduction of heat transfer. Thank you.